Okay, only 1 minute late. Welcome everyone. My name is Don Kams, and I want to welcome you to NERSC Quantum Days 2025 on behalf of our organizing committee. This year already marks the 4th edition of Quantum Days. We started in 2022 with just a single day event, about 10 presentations, and have grown it pretty organically over the past 4 years to a 3-day event this year with over 30 presenters from people from national labs, academia, and industry. And we're very excited to have you all here today. So this event started off as part of our Quantum at NERSC program, which is summarized on this roadmap, which shows 2 parallel roadmaps. On top, we see the NERSC systems roadmap, starting with all the way back with Corey in 2016, and then our current polymer system in 2020. And around that time, we started our quantum program. And some highlights that we've supported over the past 4 to 5 years are the QAS at Polymer program, where we've made access to Polymer available to people in the QAS community. This very own Quantum Days conference that sprung out of it. And then in 2023, we started in an R&D partnership with Quera Computing. In 2024, last year, we started our first user program that made access of the Quera Aquila quantum computer. And then earlier this year, we started the QCAN IBM program, which we'll all hear all about today. And then going into the next year, we'll have the NESAP for Dudna program, which will have some quantum computing teams that will target the next generation system coming online by the end of next year. And all these efforts are helping us build a community and inform us for the system after NERSC 10, which we're planning to have a quantum computing component as part of this project. So we're all very happy to have you here as part of this community. We want to support you in any way we can. So I'm looking forward to chatting with all of you during the coffee and lunch breaks to learn more about what you're working on and how NERSC can support your research going forward. So to have a brief look at the calendar for the next 3 days, today on Tuesday, we'll have the IBM Technical Exchange. The program today will consist out of tutorials and workshops delivered by IBM, as well as talks from our QCAN IBM users. As I mentioned on the previous slide, the program only started a few months ago, so I'm looking forward to the initial results being presented today. And then tomorrow we'll hear more about our users running on Quera's Aquila system, as well as updates from hardware programs at LBL, the other QAS at Polymer talks, and updates from our quantum industry partners, and similar program scheduled for Thursday. I think it's going to be a very interesting and exciting 3 days. I will not keep you any longer. I'll hand it over to Roland now to start off with the tutorials.
Good morning, everybody. Welcome to the IBM Quantum Technical Exchange part of the program. My name is Roland. I'm a quantum algorithm engineer at IBM. Today's program is going to be, I think, a nice kind of 50-50 mix of contributed research talks and sessions led by us from IBM, by myself and my colleague, Ibrahim Shehzad. Concretely, the kind of middle part of the program are going to be talks by NERSC users, often about research done on IBM hardware. And then the first session that we're doing right now and the session at the end of the day will be led by us. And the goal for these sessions that we're doing is really to try to give you as much practical information as possible about running projects on IBM's quantum technology. Specifically, for the first session, I will start by giving a talk on quantum computing at scale with IBM. will be a bit of an overview of the different steps in running a quantum computing project, including the scoping step. And then Ibrahim will take over and do a bit more of a deep dive into the question of hardware noise and how to mitigate and or suppress it. And for the session at the end of the day, it'll be a bit more interactive. We'll have a short talk explaining how our team, the quantum algorithm engineering team, can support you in your research projects on IBM hardware. But then we'll also together work through a small experiment involving error mitigation and try to get some actual runs on hardware going. And we also hope to have some just time for open discussion. Okay, so let's get started. The era we're currently in, IBM called this the era of quantum utility. And what I mean by that is, this plot is not rendering well. I'll explain later what should have been in this plot. What I mean by quantum utility is that people are now able to run calculations on our hardware that are at a scale where they're really beyond the ability of classical simulations, just brute force classical simulations to simulate these circuits. And concretely, the scale that I'm thinking of when I say this, I'm talking about circuits that have of order 100 qubits or more, and 2 qubit gate depths of, 2 qubit gate counts in the thousands. Okay, and so the plot was supposed to show that. So like being at of order 100 qubits or more, you're well past where a classical memory can fully capture the quantum state. And by going into this regime of thousands of entangling gates, you typically produce significant entanglement where you're beyond at least the reach of just out-of-the-box matrix product state simulation. Question?
What's brute force? Is tensor network brute force? Or?
Yeah, it's what I have in mind is brute force is either just like an exact state vector simulation, or also just like a very simple out-of-the-box matrix product state. Yep. And the reason I wanted to define this is that when we work with our partners, we encourage our users to target this utility scale in their project to get the most out of our hardware. Yeah, the plot was just a plot of the number of qubits versus the number of 2 qubit gates, and then identifying the region where we're in the utility regime. Okay. Another figure not showing up. Okay, if this persists. Yeah, I apologize. Give me one moment. Somehow the figures are not showing up when I'm sharing them. So I'd like to fix that because there's obviously going to be a lot of figures.
I try and
Yeah, let me just, they all show up just fine on my side.
What is the master program you use?
PowerPoint.
How about you display from PowerPoint directly?
What I was doing,
we share the screen, or we're trying.
Sorry?
Maybe we're trying to share the whole screen. We're sharing the application.
I think something got corrupted because this is I'm using Box, and I was offline for a while on the flight. I think that screwed it up. Yeah, let's give me a moment. I'm gonna fix this. I'm just downloading it again from Box. And try again now. Thanks for your patience. So moving on, this era of quantum utility, we kicked it off in 2023 with the publication of this paper. This was a nice collaboration actually between IBM and people here on campus at UC Berkeley. And in this paper, they studied a version of an icing model on a lattice that conveniently looked a lot like the topology of IBM's hardware. And we're able to get results that were competitive with the best classical methods, at least, and by running calculations on this utility scale that I highlighted. Since then, there have been many utility scale results on IBM hardware. This is just a small sample of them, but these papers, they range from high energy physics applications, quantum chemistry, optimization, and other fields. The next step from utility is quantum advantage. And so this is really where a quantum computer truly outperforms the best classical methods out there, taking away this brute force component of it. And so concretely, this is where a quantum computer would solve a problem more accurately, more cheaply, or more efficiently, or more quickly than classical methods only. Something that's sometimes overlooked, but that's also important for quantum advantage, is that there needs to be some level of validation of the results. Not something I was planning to go into in too much detail in today's sessions, but if you're interested in learning more about IBM's view on quantum advantage and what we think are some of the more promising directions, I highly recommend checking out this white paper that we published a few months ago. Okay, so that puts us with this picture of the timeline. We're in this utility era now. We predict that we'll see the first demonstrations of quantum advantage on IBM hardware in 2026. So that's coming up next year already. And then after that, the next really big milestone from us is in 2029, when we'll release the Starling chip, which will be our first chip that allows large-scale fault-tolerant quantum computing. For the sake of today's sessions, the focus is really going to be on what people can do today and in the near future on pre-fault-tolerant hardware. But for context, I just wanted to share this bigger picture. Okay, so before talking about projects, I want to talk briefly about the current state of our hardware that enables these utility scale calculations. The hardware is really one component of three that enable people to do useful work with IBM's technology stack. So in addition to the hardware, there is Qiskit, which is a collection of software for executing programs on quantum computers. Qiskit includes the Qiskit SDK, but also the runtime service. And then beyond that, there's additional software that we've made available that built on top of Qiskit. And so here I'm talking about things like Qiskit add-ons and Qiskit functions, which I'll say a bit more about later on. Okay, so the current best chip that we have made available to our premium users is the Heron chip. This was first released in 2024. It was the R1 version. It had 133 qubits. And since then, we've made additional improvements, and now there's a revision 2 and a revision 3, and both of those have 156 qubits. The coupling map of the Heron follows this heavy hex topology with a connectivity of 2 or 3 per qubit, depending on the qubit. And this is the same as the predecessor, the Eagle chip. The thing that's really new for Heron, and that's led to really big improvements, is that entangling gates are now implemented with a tunable coupler architecture. And so that's really allowed us to reduce crosstalk by a huge factor, make the gates faster, and just overall reduce the entangling gate errors.
Those gate errors, they are qubit gates.
These are 2 qubit gate errors, yes. Yeah, and in fact, so these numbers here are really from an early version of the Heron. Since then, we've kept making improvements, both in the coherence times and in gate errors. And so that led to the Heron R3. We currently have one of these devices available to our premium users. It's called IBM Pittsburgh. And these plots kind of show the level of performance. So this is a plot of the distribution of the T1 coherence times, where the red dots on top are for the Heron R3. And so you see there's a median of about 300 microseconds coherence time. Jan has a question.
Yes, going back to this crosstalk. So do you have any publicly available tools which I can run and measure the crosstalk now? Or do you publish, because you publish single qubit gates and double qubit gate, entangling qubit gates error, but never the crosstalk, or at least I don't know how to get it.
Yeah, that's right. To my knowledge, we don't have a tool that allows you to easily get that. I mean, the point is that the crosstalk is now a lot lower than it was before, but I understand you may still want to quantify it.
For example, if I transpile a circuit, I usually use like 10% of the qubits. I would like to see what is the crosstalk for this 10%, and what is the number?
Yes. We do have this holistic metric of, what's it called? The error, the 2-qubit error per layer gate. And that is based on these benchmarking circuits that really look at a chain of 100 qubits. And so the errors in there, they include things like crosstalk. So you capture it as a 2-qubit error, but it also includes the contribution from there.
Yeah, and this is my main hint about the quality of the processors. This is how I judge how good they are without running. But it would be good to have this, even if this is your metric, that I can choose on which qubit it runs. Because how do I know which one you choose? Maybe you sample them randomly everywhere, and I'm just getting a small piece of the processor. I want to see this number for this piece.
Yeah, that's fair. I'll talk about it a bit later. We do have a tutorial that allows you to benchmark each qubit individually yourself, and also the different gate errors. But it doesn't cover specifically the crosstalk. So to that, I don't have that.
There's also the noise learner you can use to learn, some parts of the noise that you can run for yourself. And then to your other question about really knowing which qubits you're using, that's information you can actually retrieve.
Okay, this I know, but I would like to know the crosstalk for this qubit.
Right.
This is my wish list.
So if I can ask another question, like how Qiskit deals with routing information and gates efficiently through this? Because yeah, it's highly non-uniform.
Yeah, so that's another thing that I was going to spend some time on also a bit later. But yeah, our transpiler is conscious of it has some passes that actually look at the errors per gate and the coherence times. And it factors that in trying to decide which qubits to map your circuit onto. You can say maybe a bit later when we come to this slide.
Since we already stopped here like for a while, when you characterize errors, for example, 2-qubit errors, do you distinguish between coherent and decoherent parts? So this 0.3%, is it over rotation or is it just decoherent decay?
It should be the combination, the total error, coherent, and
You are pretty much.
sorry.
You do randomized benchmark.
Yes, exactly. That's how we obtain them. Okay. I'm going to move on, but please continue to ask questions. This is supposed to be an interactive kind of session. So yeah, about 300 microsecond median coherence time. Same is true for the T2 time. And then for Pittsburgh, this plot, this is actually from one of these randomized benchmarking experiments, but we found that at least the best gates now have errors, the 2-qubit gates now have errors down to below 5 times 10 to the negative 4. The median is still a bit above that. It's at the time that this was done was like 1.7 times 10 to the negative 3. Okay, just kind of putting that into the larger context of the whole history since IBM first put quantum computers in the cloud in 2018, we see a pretty nice progression in terms of these 2-qubit gate errors over time. This is on a log scale. We have Pittsburgh down here, and then we're going to continue that trend going forward. Also worth putting it in the context of our hardware roadmap. So the Heron is shown here under 2024 because that's when it was first released. And then you can see that we're due for the next chip, the Nighthawk, which will release the first instance of before the end of this year. So in the next 2 months. And this is a machine we're all pretty excited about because it's really a major step up in terms of the connectivity, in terms of the coupling map of the device. I'm going to talk about that in more detail later. I see a question.
Yeah, this might be a little orthogonal, but I wanted to ask about the way that Qiskit Transpile, for example, does routing to hardware. So having actually tried to run running stuff on the Pittsburgh machine, I was told by some of the folks at IBM that when they do routing, so when you do .transpile, it finds sort of the better, like the higher coherent qubits to map to. Can you explain a little bit more how that happens? Like what's the mechanism there?
Sure. Yeah. So the transpiler is a pretty complex object with many different transpilation passes, and so there's a layout pass deciding which qubits to map your circuit to. There's routing that then helps you actually implement all the entangling gates you need in a way that's consistent with the coupling map. And then there's translation, where you express everything in terms of the actual basis gates of the device. And then there's a whole bunch of further optimization. Your question is about like choosing sort of the best qubits in terms of their hardware noise. And so there are passes in there that take a noise model of the device. That noise model is updated on a daily basis. So like it just pulls that data from the cloud, where every 24 hours, we run a benchmarking experiment and quantify the noise in each qubit and the noise of each gate. But the transpiler has that data available. And then it has a heuristic for essentially scoring different layout choices and different circuit implementations, where it tries to, the heuristic estimates the fidelity of the circuit given the noise properties of the qubits you're mapping to. And then it tries to maximize that fidelity.
Very cool. And do we have access to those noise measurements?
Yes, you do actually. I'm happy to show you offline some code for how to look at that. But you can access like all the noise properties of the individual qubits and gates. You can even pull up the history if you want to know on I don't know, on July 2nd, what was the noise model? You can pull that up as well.
Okay, thank you.
Cool. So Nighthawk, I'll talk more about the coupling map. That's the most exciting part. It has 120 qubits. And then moving forward from 2025 in the next few years, at least in terms of the devices made public, we're basically going to be scaling up from there in a modular way. So combining multiple of these 120 qubit units into larger chips with more qubits. In the background, we're also going to be developing a lot of new capabilities, including six-way couplers, couplings between qubits that are far away from each other on the chip, and a number of other things. And then all those new developments will, in the end, enable the release of this Starling device, which is our fault-tolerant quantum computing chip in 2029. And so Starling will be able to run up to 100 million gates on 200 logical qubits. Okay, so let's talk a bit about using this technology to actually run projects. And here I wanted to actually do a quick crowd survey by show of hands. How many of you have been involved in projects that involve like running calculations on actual hardware, not just simulations or theory? Okay, a majority of people, I would say, but not everybody. And then how many of those were like projects that involved IBM hardware specifically? Okay, maybe about half. Okay, that's good to know. So I'm hoping to make this useful for people who don't have much experience yet running on IBM hardware, but it should also be of use for people that have already done that. Okay, so the first step of doing a quantum computing project is, of course, to decide what scientific question you want to address and what quantum computing method are you going to bring to bear on that question. This is, of course, largely up to you. You guys are experts in your fields. But what I can do is at least provide some thoughts on what are general, interesting general directions. So these are some computational areas, 4 computational areas that we think are quite promising and worth exploring, particularly in this sort of current and near-term regime, pre-fault tolerance already. So Hamiltonian simulation, optimization, machine learning, and differential equations. And I just wanted to highlight some examples of specific applications in each of these fields. So starting with Hamiltonian simulation, a pretty exciting technique that has been developed recently is sampling-based quantum diagonalization. And so this is a method, as the name says, for diagonalizing Hamiltonians. It's an example of quantum-centric supercomputing. So it's a hybrid method that combines quantum algorithms with high-performance classical computing. And very roughly, the way it works is you use the quantum computer to generate samples in the Hilbert space of the system that you're interested in. And then those samples define a subspace of the Hilbert space. You project your Hamiltonian onto that subspace, and then you use just classical diagonalization methods to exactly diagonalize in that subspace. And so for this technique, you only use the quantum computer for this initial step of generating samples, but it's a very important step because this allows you to reduce the dimensionality to a level where you can actually tackle it with a classical computer. And you, of course, need to do this in such a way that this subspace, these samples spanning the subspace, cover most of the ground state, overlap with the ground state. So this is one example of a recent paper on this topic This was a collaboration with Recon, where they studied various quantum chemistry problems, including looking at the ground state of iron-sulfur clusters. And they were able to get solutions for chemistry problems that are significantly larger than what you could normally have tackled with just classical exact diagonalization. In optimization, one interesting direction that hasn't been studied all that much yet is that of multi-objective optimization. So where you actually have multiple objective functions that you're trying to satisfy. So here you generally can't like optimize all of these objective functions simultaneously. And so the problem now becomes to define what's called the Pareto front. So the set of solutions that each are Pareto optimal. So like a Pareto optimal solution is one where you can't improve one objective function without making at least one other objective function worse. And the reason this is a promising direction for quantum computers is that these problems become classically difficult already for very modest numbers of objective functions. And so this is a paper collaboration with Los Alamos National Lab, where they came up with a clever QAOA-based method to address this using quantum computing. Machine learning and differential equations are perhaps a bit more tentative, a bit more uncertainty into like where the advantage may lie. But in quantum machine learning, particularly quantum kernel methods are raising a lot of interest. These methods have a problem when you try to scale them up to larger algorithms, to larger numbers of qubits. They have this problem of exponential concentration. And so this paper with Ian, they addressed this problem. They solved it and were able to actually train these models on 156 qubits and get really good results for classification problems on real world data. Okay, and then finally, in differential equations, just wanted to highlight this work by our partner, Ibrahim. They developed a Qiskit function package based on this, which you can find on our platform. And they implemented a method for solving partial differential equations using variational quantum circuits. Okay, so back to the idea of like coming up with project ideas. One approach would be simply to find an interesting question in your field that can be naturally addressed by one of these methods in one of these 4 categories, and then explore that. An alternative approach, both for finding projects or for just getting some practice with quantum computing, is to look at some of the benchmarking libraries that are out there. The advantage of this is these benchmarking libraries typically have pre-vetted problems that are already been decided to be interesting and promising. And then you can also compare the quality of your results with those of other people. So I wanted to highlight 2 examples of this. First, there's this quantum optimization benchmarking library. This is the output from an optimization working group that IBM is heavily involved in. And what they did here is they identified 10 problem classes, all in the field of discrete combinatorial optimization, that they think are particularly promising for a quantum advantage. And so one of the criteria for these problems is that these are all problems that are already difficult to solve classically, even with a moderate number, even for moderate problem sizes. So I recommend checking this library out. There's also a corresponding paper on GitHub. And then another benchmarking library that's worth checking out is this Hamiltonian library. This is based on work by people, including people here at NERSC and LBL. And this is a library specifically focused on Hamiltonians relevant for quantum computing. So yeah, before moving on, I just wanted to ask if people have any questions or wanted to share any experiences on sort of their experience trying to find projects, coming up with ideas for quantum computing projects. Or any tips that people have for other people who are who haven't run any hardware projects yet.
Are there projects that you are like, wow, it'd be great if someone did this, did that?
Google World Talks. No.
That's a good project.
It's a good project.
Super cool, yeah. I personally, it's maybe a bit vague, but I find projects in the high energy physics space super interesting. So like that's to me is a really interesting direction. Okay, well, so I'll move on. A bit more practical. Once you've chosen a project and a method to use, of course, you're going to need hardware access. And so Don already mentioned this in the beginning, but it's important, it's useful to know that NERSC has a quantum computing access program since the beginning of this year. And so you can go to this link, and if you have a project idea, you can put in a proposal and ask for time on IBM hardware through that. And so if you have any questions about that, I'm sure the NERSC people in the audience are happy to explain more. Another thing that's important to do early on when you're starting a project is to do some approximate resource estimation. And so specifically, I highly recommend estimating what is the 2-qubit gate depth you're going to need, what's the number of 2-qubit gates, number of qubits, how many shots or executions, and then how much time on system will that roughly translate to. And so I thought here it might be useful to give some rough kind of benchmark numbers or reference numbers. In terms of 2-qubit gate depth, utility scale projects we're seeing, they often reach a depth of about order 100 or several hundreds. So, if you're scoping your project and you find that the only way to do anything remotely interesting is to run a 2-qubit gate depth of 10,000 or something, then probably current hardware is not ready for that project yet. Number of 2-qubit gates, I mentioned earlier when I defined utility scale, we're seeing counts in the thousands. I've even seen projects that still get good results with more than 10,000 entangling gates. But that's a good reference point to keep in mind. We recommend people to really use of order 100 or more qubits, be fully in that quantum regime and take advantage of most of the qubits on our devices. How many shots you can run, that really depends on the time on system that you have allocated. And so it's important to get an estimate of that, but it can be a tricky calculation, how many shots you need, because it'll depend on how many distinct circuits do you need to evaluate, how many sets of non-commuting observables are you trying to estimate. It depends very strongly on what kind of error mitigation methods you might be using, and then just generally on the precision that you're targeting. But when you do estimate that number, you can then convert it to time on system. And a useful rule of thumb is that we can approximately process about 4,000 shots per second on our hardware. So in practice, a little less, but that's 4,000 per second. Where it comes from is the fact that typically the time for a single execution is dominated by the so-called repetition delay, the time between finishing the previous execution and starting the next circuit. And by default, that repetition delay is set at 250 microseconds. So that gives you 4,000 per second. And then in practice, it'll be a little lower than that.
So do you have an active reset?
Sorry?
Do you have an active reset when you don't wait until everything collapses to the ground state, but forcefully?
I actually don't know the full details of the reset. Like I know, so there's this wait period of 250 microseconds. I don't know, Ibrahim, do you know if there's anything? We do. It's an active reset.
Yeah.
Thanks.
But can you use it to speed up? To have 5 kilohertz instead of 4 kilohertz?
I mean, you can definitely the user can set that rep delay, so you can adjust it and run faster, but it'll increase your state preparation errors essentially. Like the quality of your initial state for the next run will be somewhat lower.
Okay, so the reset is not shortening the state preparation time. This was, I think, the intention of the question.
No.
No. Okay, so once you're running the project, a useful way of thinking of the workflow is in this 4-step Qiskit pattern framework. The first step here is mapping your problem to qubits. And so a concrete example of this is if you're you're simulating some fermionic quantum system, then in order to map that to qubits and to still respect Fermi-Dirac statistics, you're going to need a somewhat non-trivial mapping like the Jordan-Wigner transformation. The main thing about this mapping step I just want to share is that in a lot of cases, these mappings have already been worked out. And in fact, in a lot of cases, there are good open source libraries out there that can help you with the implementation. The second step we've already talked about quite a bit. We call it optimization here, but this really refers to taking that initial circuit or initial notion of a unitary on qubits and turning it into something that can actually run on the specific backend, the specific quantum computer that you want to run it on. So a large part of this process is what we refer to as circuit transpilation or compilation. It includes the layout problem, the routing problem. I kind of forgot to mention, like earlier, an important advantage of superconducting architectures is that they're quite fast. And so kind of back to this slide earlier about the number of shots, we're often able to take a circuit that's quite noisy, but then apply error mitigation that come with a significant shot overhead and get like way improved results just by throwing a lot of shots at it. A downside of superconducting architectures right now is the connectivity is fairly modest, right? And so this transpilation step can be really important. By being clever about how you map your circuit to the actual coupling map of the device, that can potentially save you a lot in terms of the depth and therefore the hardware noise. So the default approach for doing this, tackling this problem is to use Qiskit's pass manager. You can generate one with a certain optimization level, and then you apply it to a circuit to get a transpiled circuit that can run on the hardware, and that's as optimal as this piece of code can make it. However, I always recommend, even before running this code, try to really think hard yourself about how you can most cleverly map your problem to the specific topology of the hardware. Because first of all, people often are able to come up with things that are more clever than what the transpiler can do. And secondly, sometimes you might realize that there's a small tweak you can make to your problem definition that makes it much more hardware efficient or more hardware friendly. So you can make adjustments to your problem. And then a third thing when talking about this problem that's worth being aware of is that there are additional open source packages out there. I think we have a talk later this week about Biscuit, which is a package developed here. And so it's also worth checking out these other transpilation packages.
Can I ask a question about transpilation? So
yeah,
we experienced a problem when we used fractional gates. Running transpiler once resulted with some error. And we will find out which error it was because it was like a month ago. So we filed a ticket and then you told us that we should manually transpile second time using some special one of those functions, not all of them. And the other hack was to call transpiler twice.
okay.
But then this lead to very weird labeling of the qubits. They have like double indexes. So either way, it sounds hacky. I mean, it looks hacky.
That's an interesting question. Do you mind if we take that offline? I'd love to get some more details on that and look into that. Yeah, let's discuss that. Okay, so I realized that I want to leave enough time for Ibrahim, so let me just briefly talk about this and then hand it over. One thing that's going to make this whole mapping or this optimization problem a lot easier is the coupling map of this Nighthawk device that we're releasing soon. So this will have a square lattice topology that, of course, means a connectivity of 4 per qubit, which is a lot better than the heavy hex. But it's also just a topology that's naturally matches to a lot of real-world problems that people are interested in. So the improvement in the number of 2-qubit layers that you can get from going from a heavy hex to square lattice depends on the problem, but in the worst case scenarios, it can be a factor of up to 16 times. This can really allow you to run significantly larger calculations. Okay, yeah, I think I'll hand it over to Ibrahim. Most of the rest of what I had to say after step 1 and 2, there's step 3 and 4. Sorry. And so like we've talked about the first 2 steps. Step 3 is actually executing, and then step 4 is post-processing. But a lot of the topics that are relevant for this are related to handling noise, are related to error mitigation and error suppression. And so that's what Ibrahim is going to talk about now. While Ibrahim sets up, if there's any questions, he'll try to answer them.
Question.
Oh, yeah.
The new architecture with more connections per qubit, is there any expected like differences in fidelities or improvements, declines and changes? Like gate fidelities?
Not that I know of. Gate fidelities should be at the level of the latest Herons or better, to my knowledge, but I haven't seen the specs yet of what's actually going to be released.
Yeah, those will come out together with the chip.
When will the new architecture be available on the cloud platform?
Well, before the end of 2025.
Okay.
But I don't know, Victoria, if you have a better date.
At this point, we don't have a better date, but we are rushing to get this.
Christmas.
Everybody goes online around Christmas.
This is the first time you might have to restart Zoom application after you've given it.
But I think it's best if I share a PDF, right?
That was not so much a PowerPoint issue, it was a box issue.
Then I can do.
So if you use that, I think you have to first go into presentation mode and then you share it.
Share the right screen.
Yeah. Then you have like multiple choices for yours. And then you said something. No, there was some option earlier on of turning off the microphone.
All right.
Just get past
I
that.
think it's fine.
Okay.
You're good.
Wow, very nice. Apologies for the delay. All right, so I'm gonna pick up where Roland left off. My name is Ibrahim. I'm part of the same team as Roland. And the goal of the second half of this presentation will be twofold, sort of walk you through the common sources of noise on quantum computers, and then the tools that the IBM stack gives you access to mitigate and suppress these sources of noise. And really the goal is to try and convince you that using these techniques, quantum computers today are primed to deliver utility and scientific breakthroughs. And I see experts in the audience who've already worked a lot with these things and maybe people who haven't worked with these things so much. So I'd like for everyone to take something away from this presentation. So for people who have not worked with these things before, please stop me and ask as many questions as possible. And for people who have, if you have anecdotes or anything that you've run into, issues, problems, good feedback, bad feedback, let's discuss that as well. All right. So I know Roland shared the slide just a little while ago, but to set the context for this talk, this 4-step process or pattern is how we like to think about quantum computation problems at IBM. So you map, optimize, execute, and post-process. And everything I'll have to say in this talk will be about this step 3 here, where you actually execute your jobs on hardware. And through Qiskit IBM Runtime, which is our client for accessing hardware, you have 2 primitives, the sampler and the estimator. The sampler is more for sampling-based problems, and the estimator gives you access directly to expectation values. And there's different tools you can use for each one. You can also combine them. All right, so this is a brief outline. So we'll discuss noise, then error suppression techniques, which go more with the sampler. And I'll say more about what these are, what they do, where they come from. Then error mitigation techniques, which go more with the estimator. Again, more details on that. And then finally, I'll talk about how you can just combine them in a very seamless way. And I'll briefly discuss error detection techniques that kind of are relevant in, for both of these primitives. All right, so there's 3, so the way I like to think about it, there's 3 main, or you can classify the sources of noise in quantum systems into 3 main categories. The first of which are fall under this umbrella of environmental noise, which you can model as a bath system coupling. So it covers both the decoherence of qubits, something that's captured by T1 and T2 times, but also crosstalk that you see, for example, when you have idling qubits interacting with their neighbors. And then as Roland shared, this issue is actually largely mitigated on the most recent IBM devices, the Heron devices. But there's still ways in which you can mitigate it even further. Now this was the first source of noise, like I said, environmental noise modeled as a bath system coupling. Then the second source is, of course, readout noise caused by imperfect measurements. And then the third source is gate errors, caused by imperfect operations. So these can be coherent or incoherent errors. And one thing I'd like to highlight here, maybe this is already something people know well, is these dashboards here. You saw that on all 3 of these slides, I could actually see at most 24 hours old data that told me what these errors look like on my device. And with these, I can even plot it out in a different way and see, what, for example, 2-qubit error each of these links corresponds to, or 1-qubit gates and stuff like that, or T1, T2 for the individual qubits. So anybody who uses this can actually access this data, pull this data from these dashboards and use it in their workflow. So it's pretty handy, I'd say. Yes.
So you said the data is valid for 24 hours. So is it correct that you do recalibration of all the qubits every 24 hours?
I believe so.
And then my question is, well, I know in the past, Rigetti did it every 6 hours or something like that because they had a lot of drifts. So let me ask this. So immediately after recalibration and 23 hours after recalibration, how close are these 2 quantum systems? Do they drift a lot or not? I mean, can I rely on this data after 23 hours or do I need to wait?
It's a good question. And I will say it also depends on the underlying architecture. So for the more recent devices, it's this issue with drift has been largely mitigated, but there are actually tools that you can, or workflows that you can run, and I can walk you through them offline, where you can run this for yourself as well. So track over a few hour time, or maybe let's say 2 days or so, how this data is drifted, or within a 24-hour window as well. So you can actually track that. From what I know, having not worked too closely with the hardware or on calibrations, is that on the Heron devices, it's a lot lower, this problem. On maybe the initial Eagle devices, it was more significant than what it is now. Yes, please.
Are the readout error monitored on a daily or hourly basis?
Yes.
What's the time scale?
Frequency? I'm not sure. I want to say it's the same, but I could.
I think it's the same. I think it's daily.
24 hours.
Yeah.
Yes, Roland.
I've actually seen that it's monitored on an hourly basis.
The readout errors?
You go
on the website, like for all the gates and the readouts.
Interesting.
Like it will say updated 45 minutes ago, an hour later it'll be updated 15 minutes ago or something.
Okay, interesting. I'll take a look at that then. Okay. Well, thanks for the feedback. Yeah. Any other questions? All right. So just to recap, we've discussed three main sources of noise: gate errors, environmental noise, and then imperfect measurement or measurement errors. And really the techniques that we have access to. So before, fault tolerance, which is where we're eventually headed, the tools that we can use fall into two main categories. So techniques that minimize the impact of noise sort of, during the execution, fall under the umbrella of error suppression techniques. And there's two main techniques that we have access to or provide access to. They're called dynamical decoupling and Pauli twirling. I'll go into the theory a little bit. And then error mitigation techniques that have more of a role in like the post-execution step. So that's where they use more of the resources. And there's two main ones, Z0 noise extrapolation and twirl readout error extinction or TREX. I will say that, this is something that's been talked about in a lot of papers recently. It's not the case that these techniques will stop being relevant as soon as we get to fault tolerance. Like they will have a role in actually working alongside for fault tolerance. And so it's important that we build expertise and get working experience with these techniques, given that we can use them right away.
Sorry, why would they matter after fault tolerance?
Also, fault tolerance really works if you have errors below a certain threshold, right? Like you want errors below a certain threshold, and then you can run long computations. And this can actually help you do that, get below a certain threshold, and then that's where, you bear the fruits of error correction.
But both these techniques, some of them require, for example, sampling. That is something you don't want to do as much on an error corrector system, or requires like long, chains of T's, like a lot of magic to make them happen.
I'm not sure why.
No, I'm just asking if it's the case. It's not a trick question.
No, I don't think so. I don't think so. I mean, so for example, like when you do error correction, there's syndrome measurements that you make. So you do sample in that sense. For example, something that you're doing during the execution, like getting rid of idling errors, dynamical decoupling or something, that's going to remain relevant no matter what.
Okay.
Does that make sense? Kind of.
Yeah. Okay.
And so then there's error detection, which I'll have more to say about at the end, which sort of fits in. It sort of works with both of these paradigms, and then we'll see examples of each towards the end. All right. So with regards to the three main sources of noise that I discussed, this is where these techniques fall. So Pauli twirling and ZNE help mitigate gate errors. For measurement errors or readout errors, you have TREX. And for environmental errors, you have dynamical decoupling. So this is the map, really, to keep in mind. So let's dive briefly into our suppression techniques. How am I doing on time? You have half an hour? Okay. So dynamical decoupling, really, the idea that you want to keep in mind is at a very intuitive level, what it does is it keeps the qubits busy while there's operations happening on other qubits. Now, you don't want to change the logical operation happening on these qubits, so whatever gates you apply have to add up to the identity. So what you can do, for example, is if this qubit has some operation going on, and this one is actually would have been staying unoccupied, you can insert gates that sum up to the identity. So you have X and X and X and X, or X, Y, X, Y, and stuff, and so on and so forth. And it gets rid also of crosstalk noise, like the ZZ coupling that's always on, at least on the previous generation of these devices. So it cancels out that effect. With all of these techniques, one caveat that we'll discuss is there's a balance to be found, right? So even though in principle you're applying the identity, you are applying gates on the actual device. And some of these gates have their own inherent noise as well. And so you don't want to, you want to sort of find the right balance between mitigating the noise that you have and versus introducing noise by doing these operations. So the goal here is basically to show you that if you were to use these techniques in your own workflow, there's really not a lot that you would need to do yourself. So through Qiskit and Qiskit IBM runtime, you can actually very seamlessly turn these options on. You can tune them as much as you like if you have, deep knowledge of these techniques or the hardware. So you can pick your favorite sequence. You can pick where it's placed. You can decide what happens to the slack, or you can just let it do it itself just by picking some default options. So, you simply turn on a flag that says true. And then if you were to do nothing else, it would pick some default settings, or you could pick your own sequence. You could schedule it like ASAP or ALAP, put slack in the middle, and so on and so forth. So it really is basically very seamlessly used in this way. And this applies basically to all the other techniques as well, as I'll show in just a second. For Pauli twirling, really the idea is you want to convert sort of arbitrary noise channels into Pauli noise, which grow linearly with the depth of the circuit, versus so coherent noise would grow quadratically, which is faster. And the idea is to get rid of that so that your noise actually accumulates slower as you go up in depth. And again, the idea here is you're not changing the logical operation. So as you can show by working through some of these identities, your logical circuit, your logical unitary stays the same. It's your noise that's actually been shaped. And it's basically by applying sort of random Pauli gates, before and after these operations, so like twirling them with Pauli gates, convert it into a random Pauli channel. And the idea is that Pauli noise actually accumulates in a much slower way. So you see the benefits of that. All right. Yeah. So for example, if you specify a certain number of shots in your circuit and you turn on Pauli twirling, what it'll do is it'll sort of divide it up into different instances where there's random Pauli gates that are applied before and after the noise channel, before and after the noisy gate, and then you average over it to shape the noise in that way. And then again here as well, it's the same set of features. You can just do the vanilla thing and turn on Pauli twirling for gates just by setting a flag to true, or you can pick how many shots you want to do per randomization, or how many randomizations you want to do, or how you want to twirl your circuit. You want to sort of twirl all the active qubits, or all qubits, or active AQM, which is, I believe, that's the default setting here. So it can be as fine-grained as you want it, or you can just let Qiskit decide for you as well. Yes.
So some time ago, I tried those options and they work only on the hardware. I could not use them on a fake simulator. Has this changed?
So do you mean like applying error mitigation on simulations?
Yes.
I don't believe it's changed, but it's something that's actively discussed, because we do see the some use for it.
And what is the reason it was not enabled in the first place?
I think so overall, from what I understand, the idea is at the end of the day, you learn about the hardware by actually running on the hardware. Like there's only so far that simulations can take you. And so even with error mitigation techniques, when you actually have experience with running them on the hardware is when you learn the most. So that was the main idea, you use them when you run on hardware versus getting tied to a simulator, which will only take you so far, it won't be able to go beyond a certain size and stuff.
So it might be outdated, but anyways, so are all these techniques transpiler optimization safe? What I mean by that, if I say, please transpile the circuit and do the maximum level optimization, and transpile says, hey, look, you have qubit number 0 and you do 4x gates, which is pretty much identity. So why do you ever do it? Just replace it with identity. So in the past, it definitely was the case, and I needed to use barriers to basically enforce like doing these gates for nothing.
Yeah.
So I mean,
It is
right now?
Yes. So to your question, I think what you're saying is, if in dynamical decoupling I put 2 X gates next to each other, will the transpiler just cancel and not do it? It is transpiler safe for sure. It will.
I guess it's safe because of the order in which you run these things. So in a typical workflow, you would first transpile your circuit, and then you submit it to the sampler or the estimator with some flags for Pauli twirling, maybe dynamical decoupling. So like that gets applied after you've already done your transpilation. So then the transpiler is not going to come in after that again and remove these things that are equal to the identity.
Yeah, that's an important point. I guess previously you didn't have to submit circuits that were transpiled. And right now, you have to submit ISA circuits. And so
Well, I mean, yeah, it was done in a different way. So basically, if we have a circuit and we want to run it, we could say, look, for example, we do Hamiltonian evolution, and then we do a bunch of time steps. And if we pile all this stuff together, push it in the transpiler, it says, oh, I know it will be like all unit gates. So you don't even need to do anything. I'll collapse everything to unit.
Yeah.
And then we put a lot of barriers so that we prevent it from doing it. And my question was like, if I manually do dynamical decoupling, and say I just add a bunch of XK to registry 1, and then push it in the transpiler, will it just collapse everything to unity? Or does it say
So
no?
that's a subtle point. I think in that case, you would still, like if you're doing it by hand, then you would still want to be careful and sort of like still specify barriers and not have it like combine them. But with the techniques that are available through scheduling time, when you do dynamical decoupling through this, then because of the order of events, like it transpiles, and then when the execution actually happens, that's when these things are inserted. So there's no, these things don't conflict and things like that. All right. So that's gate twirling. And so, both of those techniques fell under error suppression, which are things that you use with the sampler. And then now I'm going to move on to error mitigation techniques. So remember, they do most of the heavy lifting in the post-process, sort of the after execution step. And I'll go into the details of these one by one. But just to keep in mind that so that your overall map stays clear, these are the techniques you use with the sampler. And these are techniques that you use with the estimator. You can also use both of these with the estimator as well, but not the other way around. All right, yeah, so I'll talk about PC briefly as well. So so the first error mitigation technique that I'll discuss is T-Rex. And here the idea is that readout errors can be modeled as the probability distribution of the outcomes that you observe so you can model it as a stochastic matrix acting on the ideal probability distribution. And really the idea at an intuitive level is to try and invert that matrix. Now that's not always feasible. And how you get around it is by twirling your measurement channel in this way. So if you're measuring things in a Z basis, what you do is you apply a C naught, then you do a measurement, and then you classically bit flip sort of so that the overall operation still remains the same. But what it does is it actually diagonalizes the error transfer matrix of your the measurement error transfer matrix. And what that means is per Z observable, your error is now reduced just to an overall prefactor that you can calculate by running identity circuits, really. And then once you have that, you can just divide out by that. But as is clear from this expression here, this only works for expectation value. So you can't do this with raw samples, which is why T-Rex is only available for the estimator. Any questions at this stage? Yes.
The diagonalization is exponentially high.
So again, yeah. So if you were to invert it completely, yes. But the idea here is you specify some kind of a sampling budget, so it's not a perfect diagonalization. And yeah.
Is it M3 based or is it?
Yeah. So M3 actually works with raw samples. And I want to say this is still different from that, but I need to give you a better answer. I'd have to look into it.
Yeah, this is a bit different. It's based on a calibration circuit method. So you do this twirling that actually diagonalizes the Pauli transfer matrix of the readout noise, and then the expectation value of a given Pauli string will just get some multiplicative factor due to the readout noise, and then you can estimate that multiplicative factor from running a calibration circuit where you literally just do nothing except measurement, and then once you have that calibration factor, you use it to correct the results in your circuit that you're actually interested in. So it's conceptually quite similar to a technique that people use even beyond readout error mitigation called operator decoherence renormalization.
Any other questions? Okay. So, and then as with the other techniques, it's a fairly simple block of code that you actually need to do to, use this technique TRX. It's, again, this line would suffice. You don't have to pick these if you don't want to, but you can if you understand it more natively and, you want to handpick some of these parameters. So the second technique I'll discuss is zero noise extrapolation, and sort of at an intuitive level, the idea is it's a two-step process. What you do is you amplify the noise of your circuit so that you get more data points, and then you try and extrapolate back to, the zero noise value, and you can do different fits depending on, the problem that you're considering and what you understand about the problem. I'll have a little bit more to say on that. But the two main ways in which you can do the first step, which is noise amplification through Qiskit IBM runtime, is one of them is called gatefolding, where you, for example, if you were to implement this unitary, it's logically equivalent to this or this, but each time you add this unitary on the actual hardware, you're adding more noise. So you're getting an amplified noise version of your expectation values. And so that gives you these data points that I showed here on this graph. And then once you have those data points, you can, like I said, extrapolate back. So this would be the default way of doing it. However, a more hardware intensive way, but maybe a more accurate way to do this is to do what's called probabilistic error amplification, where you actually learn the noise on the hardware using this thing I alluded to earlier. It's called the noise learner. So first you shape the noise. You do Pauli twirling so that it gets projected down to a sparse polylit channel. Then you learn the noise using a tool called the noise learner, which actually you can access independent of this workflow as well. You wanted to learn the noise and understand it. Once you've learned the noise, then you insert many copies of it, also as a way to sort of get these more data points at higher values of noise. And that would be the error amplification step. And then you can basically go back and go back to zero noise. So as I alluded to earlier, this tool that we use here at MPEA, the noise learner, you don't have to use it in the context of ZNE, right? To your question, if you're interested in understanding the noise, not on a 24-hour timescale, but as of right now on the hardware, you can run this tool and it'll give you the error rates, assuming a sparse polylit channel, and you can go from there. So once this is done, the next step is to really figure out how you want to extrapolate back to zero noise, and that's a very non-trivial step. It's not at all obvious if you should use a linear fit or an exponential fit or whatnot, and you kind of have to. There's trade-offs to both of them, and really the heuristic that I keep in mind is when you run ZNE on Qiskit, it actually tells you the standard deviations for each fit. So what you can do, for example, is you can specify multiple extrapolators. It can be exponential, linear, it can be higher polynomials. It can be any one of them or multiple ones. And when you run this, it actually tells you the standard deviations for each fit. And often what I find to be useful is if for a certain fit, the standard deviations are just way too high, then you don't really trust that fit, right? So you go with the one that has a lower standard deviation, is more well-behaved throughout the fit. And then you pick that. But really, it also depends on the problem at hand. The other thing you have to be mindful of is, again, like I said, you're actually amplifying the noise when you run something on hardware. So you don't want to amplify it to a point where you cannot recover any signal, right? When you pick these noise factors, you're telling it, give me data points at the original noise value, but then 3 times the noise value or 5 times the noise value. And if your circuit was deep to begin with, there's very little hope that you'll get any useful signal at these values. So you kind of have to pick those values in a smart way. And a good thing is you can actually pick fractional values as well. You pick like 1, 1.5, 1.3, 1.6, especially for deeper circuits. That's usually the better way to go. And again, we'll see an example of this in the tutorial later on, but you can tell it to give you multiple fits, and then you can pick which one works best.
Can you discuss for this example the shot overhead? So
Right.
for the ZNE, I'm paying for every version of noise.
Yes.
And how about the next one, this amplifier?
So the amplify, okay, good. So, right, like you said, if I have 3 noise factors, my shot budget gets multiplied. So if I have 10,000 shots, it'll be 30,000 shots at the end of it. For this gatefolding versus PEA, the overhead for PEA is significantly larger. You need more experiments to sort of accurately learn the noise. Whereas for gatefolding, it by default does not change the shot overhead. It's just adding more gates. The additional shot overhead just comes from the factors that you've picked. And yeah, so again, so the reason why the reason why PEA has an additional overhead is because there's extra executions that you need when you're learning this noise. And you can specify a budget and say, this is the most I'm willing to accept. Maybe I'll show a code block of that here somewhere. Yeah, basically here. But then it can like fit things in within your budget. But then again, it may not be the most accurate noise model that it learns if you have like fewer shots.
So what is the default you recommend?
The default for these things, you mean? Right.
This noise amplifier, which you said that the overhead is even larger, but you didn't say how much larger.
Right. It depends on the circuit. And I would say that if you're deciding between gatefolding and PEA, then think for a second. Yeah, maybe part of your question is, if you don't specify these numbers, what are the default values that are set? And I think these are actually pretty reflective of the default values, but I'd have to double check. I can get back to you on that. Yes.
In your experience, when we're running stuff on the estimator and using ZNE and T-Rex and these error mitigation techniques, assuming, let's say we have a 20 qubit circuit, what depths have you seen that give back on the estimator like a reasonable degree of signal?
Yeah, so I want to say there's no one number that I can give.
Sure.
Depends on the structure of the circuit.
Yeah.
Let's
say like relatively sparse circuit.
So I would then phrase that more in terms of the number of gates than the number of layers. And like Roland said, I think up to like order thousands of gates can handle executions pretty well. But that would be the number I'd give, having not looked at the exact problem. Yes, Roland.
Is this noise learner for like a brick wall circuit or?
Works for any circuit. So it has to be, actually, I don't think we have to layer the circuit when you give it to the noise learner. So actually, yeah, so it works. It basically layers it, itself. And then
It finds the layers of 2 qubit gates, right? And then learns the noise for each of those layers.
So does it give you like the sparse poly noise channel that would act at the end of your circuit? Or is it like per layer?
Per layer, per unique layer.
Does it tell you like how much systematic error there is in assuming that it is a sparse poly?
No, it just assumes that is, yeah. I think that there's been work on that and people are looking into it. Yeah, that's a very good point.
So can you say more in detail what actually it does? It inserts extra gate for every layer on every qubit? Is it a single qubit gate or 2 qubit gates?
It's yes, it's actually given here.
It's just cycle benchmark.
Oh,
okay.
Does that answer your question? All right, so this is certainly one way to implement all of these techniques that I discussed. You can, again, if you wanted more native control, you can turn these options on one by one in as much detail as you like. Or if you are, you're happy to trust whatever Qiskit does by default, then you don't actually have to do any of this. If you're using the estimator, what you can do is just specify this one line here, options.resilience level equals 2. And resilience level 2 actually turns on basically everything that we just discussed. You can set it to 1. For example, if you don't want ZNE, you don't want this extra shot overhead or whatever, then you can restrict it and set it to 1, or you can do no mitigation and then turn things on one by one by hand, if you like.
Does Qiskit turn on any error mitigation by default, like if I don't go to any of these options?
So if no, I mean none of these would be implemented if you for example, if your optimization level is set to, sorry, your resilience level is set to 0 and you don't turn anything on by hand, then no.
Because I know for sure, like a year ago, 2 years ago, at least ZME was on, because when I ran like super small test programs, I could get probability greater than unit or less than 0. So that's like notion of ZME.
We do have that resilience level flag that you can set to 0, 1, or 2, and they correspond to some like preset settings. That like 0 is nothing, and then 1 is a little bit of error mitigation, and 2 is a lot.
I guess you're saying in your
Is it
case.
possible that you had that turned on, maybe resilience level is set to 1 or 2?
Well, it's hard to remember because, yeah, it was either 1 or 2 years ago, and
Yeah.
Qiskit is updated so frequently.
Yeah, this is what
all
I
the
think.
notebooks get absolutely like in a year.
Well, we try and make sure it's backward compatible in general, so that, you know, there are no breaking, not a lot of breaking changes. But I think in your, I would suspect that it's not turned on, in that case, it wasn't turned on. And I guess what you're saying is you were seeing probabilities that were greater than 1 or something in some of.
Less than 0.
Wow. I'd be interested to look at what was going on. I haven't seen that in my experience. Okay. So I wanted to separately discuss probabilistic error cancellation, which is similar in spirit to PEA for at least the first step, which is, again, you shape the noise and you learn the noise. And this is the expression for a sparse party in-batch channel. So again, you basically, what you're learning are these omega sub k parameters, and then you invert them in a quasi-probabilistic way. The reason why I've dedicated a separate slide to PEC is twofold. First is it actually gives you a bias-free estimator, which is a significant guarantee to have. For something like ZNE, you know, you get some value, and if you haven't tracked your error bounds, it's not always clear if you should trust it. But with PEC, if you can, you know, run it and, you know, digest the shot overhead, then it guarantees a bias-free estimator. Now, there's no free lunch. It comes at the cost of increased variance, which you have to suppress by taking more shots. And the number of shots actually scales exponentially with the number of unique 2-qubit layers. So you want to be mindful of that. However, you can still restrict this. You can tell it, you know, this is the most overhead I'm willing to accommodate. Just, you know, don't go beyond that. And it's simple enough to implement in this way. Thank you. And then I guess the other thing was that PEC was actually one of the techniques that was used in this utility paper that Roland referred to. So it was you know, it worked out pretty well in that case. I want to talk really briefly now about quantum error detection. And here, I mean, this is not to say that these are the only 2 modalities of error detection, but these are the 2 I wanted to highlight. There was an IBM paper about this recently about using Pauli check sandwiching to detect errors in you know, inside your circuit. It has modest overheads compared to both QEC and quantum error mitigation. However, because you're post-selecting, you know, your post-selection rate actually goes down with the depth of the circuit. So you need many, many more shots to sort of get back to, you know, that same level, maybe that same signal. But it's something you can sort of before you get to full fault tolerance. It's like it's something similar in spirit to error correction that you can use. And really, what you do is based on phase kickback, you have an ancilla that you apply a controlled operation to with the rest of your circuit, and if you measure a certain thing, you actually discard a certain shot. So you're actively throwing out shots based on these syndrome measurements. The second modality is actually very interesting from, for example, like a physics perspective, which is if you know something about the symmetry of a problem, if you're calculating like, you know, particle numbers or your occupation numbers for certain energy levels, and if you measure a bit string that actually contradicts that, then you know that that thing has to be thrown out, right? So if you know that you were in the n=2 particle sector, but you get this bit string, so one would be, you know, telling you, for example, so the Hamming weight is telling you how many particles you have, but if you have a Hamming weight of 1, that's telling you clearly this cannot be right because, you know, your symmetries had ensured that you were in the 2 particle sector, but you're measuring something that has Hamming weight 1, so there's clearly been an error. So this gets flagged and you toss it out. This is actually also something that's used in sampling-based quantum diagonalization, which is why, for example, for chemistry problems where you know what the occupation numbers should be, this comes in very handy, and it's implemented in this SQD add-on that's now available through Qiskit as well. Okay, so I know that this was a lot, but what I want to conclude with, I have 2 minutes. Okay, great, thanks. Is actually something. It's more a call to action than anything really, and you know, our roadmap is that we want to get to quantum advantage by the end of next year, working with practitioners and researchers like yourselves. And in this paper that IBM put out earlier this year, they outlined a framework for getting to quantum advantage. But the thing I want to highlight from this paper here is this need for validation. When you run a quantum experiment, you get certain outputs. How do you know that that's something that's reasonable and sensible? And one important part of doing that, especially if you're using error mitigation, is having some kind of error bounds on these error mitigation techniques. So for certain techniques, you can write down Hoeffding inequalities for PEC, for T-Rex, and you can actually derive these bounds and say, if this is my shot budget, and I do these many circuit executions, what's the most error that I can have? For some other techniques, there's some preliminary work, but it's something that needs to be worked on and more actively developed if we are to develop more trust in these techniques going forward. So this is more like just highlighting the fact that people who work on these things should also keep this aspect in mind. This needs some work to build more trust on, derive rigorous error bounds on stuff. This is again why PEC is so good, because it gives you a bias-free estimator. You can actually rigorously prove that. So finally, just to end, this is a slide that Roland shared as well, but what I want to emphasize here is the stuff that I discussed is not just theoretical fluff. I guess I'm a theorist, so I can say that, but it's not stuff you would never use. This was used in this paper that IBM put out, the utility paper, these techniques. So ZNE was used, PEC was used, and they saw good results from that. But also in all of these papers that have been put out since then. So at utility scale, order 1,000 gates, 2-qubit gates, and then hundreds of qubits, they're all using these techniques. So for the last several years, people have been working with these techniques. That's why we work so hard to make them easy to implement through runtime and through Qiskit. And that's why I would encourage all of you to try them as well. With that, I'll end, and thank you for your time. Happy to take any questions.